Hi, I'm Ayush. I'm an applied scientist at Amazon Alexa Natural Understanding. Today I will present our work on class-agnostic object detection. Conventional object detectors perform well at detecting object types that they have been trained for, but they are limited to scene object types primarily due to the cost of annotating large datasets for detection purposes, which hinders the adoption of detectors in real-world applications such as large-scale object matching, visual relation prediction, etc. We propose class-agnostic object detection as a new problem domain for localizing objects irrespective of their types. Models developed for this task would have to predict bounding boxes for all objects in a given image, but not their object classes. The resulting boxes would then be consumed by downstream modules for application-specific recognition, retrieval, etc. In this work, we established this new field and proposed baseline models, a new adversarially trained detection model, and experiment protocols for benchmarking current and future research. Here is an illustrative example. A class-aware model detects only known objects, but an agnostic one should detect all. The problem definition presents a few straightforward baseline models. These are a region proposal network of a two-stage detector, a conventional class-aware detector, a pre-trained class-aware detector that is fine-tuned for the object versus not task, and a detection model trained from scratch for the object versus not task. However, class-aware detection requires learning class distinguishing features to identify specific kinds of objects while localizing them. In contrast, class-agnostic detection requires features that distinguish objects from background and object instances from each other. Hence, class distinguishing features actually hinder generalization to unseen objects. In order to learn class-agnostic features and ignore class distinguishing features, naively training a class-aware detector for the object versus not task is not sufficient. We need to explicitly train the model to ignore class distinguishing features. To that end, we present an adversarial learning framework for class-agnostic object detection. The method can be generally applied as an add-on to any existing detection model, whether one-stage or two-stage. The framework splits a detection model into an upstream part that performs feature extraction and a downstream part that includes the classification and box regression branches. The classification task is switched from object type classification to object versus not, and an adversarial discriminator branch is added that penalizes the model if object class can be predicted from the features. The discriminator is updated 5 times for every update to the rest of the model in our experiments. We first evaluate the model on its generalization capability to unseen objects. We perform 2 sets of experiments. For the first experiment, we split the VOC dataset into 2 parts, 17 seen classes and 3 unseen classes, where the unseen classes are chosen as easy, medium, and hard cases based on the confusion matrix of a pre-trained SST model. The models are trained on the seen set and evaluated on the unseen VOC set. Models are additionally evaluated on non-overlapping classes in the MS-COCO dataset. In the second set of experiments, models are trained on MS-COCO and evaluated on non-overlapping classes of OpenImages v6. Results show that region proposal does not work well at class-agnostic object detection as expected. Class-agnostic models in general perform better than class-aware models. Our class-agnostic model, trained adversarially from scratch, performs the best for both faster RCNN and SST. Class-agnostic models fine-tuned from pre-trained class-aware models do not perform well. This is potentially due to the difficulty of unlearning class distinguishing features while learning object versus not features. We further evaluate the model for downstream utility through object recognition on the ObjectNet dataset. Detection models are used to generate top-M detections, which are then used to crop images and feed to ImageNet pre-trained classifiers. We use 2 metrics for evaluation: accuracy at different values of M and the accuracy when using the crop with the highest overlap with the ground truth box. Comparing class-aware model and our adversarial class-agnostic models, we find that our model outperforms the class-aware baseline across the board, irrespective of the recognition model used. In conclusion, we have established a new direction of class-agnostic object detection, provided experiment protocols and baseline models, and presented a new adversarially trained class-agnostic model. Our adversarial model performs the best at both generalization to unseen object types and downstream utility. Future work has several possibilities, including but not limited to further refinement of the problem formulation, improved and additional experiment protocols, and new methods for class-agnostic object detection.